Hello Year 12, welcome to the next video here in our trigonometry section. And we are looking today at the sine rule, which is a wonderful thing, something you haven't done before, and it does have many useful applications when we're solving some geometrical problems. But first of all, what we want to look at are some conventions when we're naming sides and vertices, corners of a triangle. Right, convention that we've used before, but just a reminder, we use uppercase letters, normally Latin characters, A, B, C, D, a regular alphabet, for vertices, right? Capitals, right, like this. And for a triangle, right, we use the lowercase, the corresponding lowercase letter for the opposite side, right? So if that's A there, this is a lowercase a here. So capitals for the corners, lowercase for the sides, A, B, and C, like this. Okay, so that's our naming convention, which leads us into, here's the sine rule. Now, I don't care too much about the C part, right? You can name your corners A, B, and C whichever way you like, so you really only need to do two of them. A over sine A equals B over sine B. This side here, divided by the sine of this angle here, S-I-N-E, right? The length of this side divided by the sine of this angle is equal to the length of this side divided by the sine of this angle. Right? This is a helpful way of writing our equation, our formula, if we want to find a side. Okay. Now for this, we always need to sort of make sure we get a bit of a cross shape. Okay, we need opposite sides and angles. If I've got three of those four things, I'll find the fourth. Okay. And let's look at an example and see how that works. Oh, now this would be right. We get a complicated example first up. Why is this complicated? Well, I've got this pair here. That's wonderful. If nothing else, what that really does is establishes the ratio for us, right? Because that ratio of the side to the sine of the angle is a constant, right, for any triangle. But I don't have another pair, right? I want to find M here, right? To find M, I'm going to need that angle there. I need this angle here. I don't have that. But I know that my triangle interior angles add up to 180. So 65 plus 75 is 140. So this angle here must be, let me just make a little bit of space there. This angle is going to be 40 degrees. Right, and I'm pretty happy just to write that on there. Right, that's not too complicated. So now I know that M over sine 40 equals 16 over sine 65. And I rearrange this a little bit, multiply both sides by the sine of 40, and I get M equals 16 sine 40 over sine 65 degrees. The calculator comes out. Watch how I type this in, because there is some tricky syntax with the calculator. Sometimes it tries to do something that doesn't make a lot of sense. 16 times sine 40 equals, right, that's what I would do, and then divided by the sine of 65 equals 11.3 is three significant figures. 11.3 meters, three significant figures. Okay, this is nice. We can use trigonometry now without a right angle triangle. There we go. Wonderful. And here is a second example here. Now I've got some words. Georgia looks south. Observe an aeroplane. An angle of elevation of 60 degrees. So 60 degrees above the horizontal. Wow. Sure. So these people are 20 kilometers apart. 20 kilometers apart. I have some angles here. Righto. And I want to know, right, my diagram helps out here. I want to know how long this side is. I want to know how far Henrietta is from the plane. Right. Now, I kind of sort of have this pair here going on. I want to find that side. I've got the opposite angle. That's good. Once again, I've got this side. I don't have that angle. Much easier to find the angle than the side. Now, 60 plus 75 is 135. So I need an extra 45 degrees in here. Right. So now I know that x over sine 60 equals 20 over sine 45. Oh, yeah. Therefore, that's the way to start. That much working. We can go from there to x equals 20 sine 60 on sine 45 to the nearest meter. These are in kilometers, so I need 3 decimal places here. Out comes the calculator. 20 times the sine of 60 equals, divided by the sine of 45 equals, now 24.495. Right. My answer is in kilometers, but it's to the nearest meter, which is the 3rd decimal place there. Rightio, that's using the sine rule. Now, we can also use the sine rule to find an angle. I'm going to chuck that in this video. That'll be fine. Now, equally, a over sine A equals b over sine B, or flip it upside down, sine A over A equals sine B over B. Rightio? Sine A over A, sine B over B. Right. In fact, I'm going to put a line through this, and I'm going to say we can also, with the angle on top, we didn't rewrite that. Sine A over A equals sine B over B. Now, this is better if I'm finding an angle. The thing that I want to find, it's best if I have that in the top left of this formula here, because when I go to rearrange it to make that the subject, right, there's the least amount of work if I do that. So, top left is what you want to find. Just be careful with obtuse angles. We've talked about that a little bit before. We'll see an example of this somewhere along the line. Now, what I want to find is the size of that angle there. It's not going to be obtuse because I've already got 110 there, so it has to be acute. I have, right, opposite sides and angles. Great, everything's set up nicely. So, sine theta, angle Q. It's not the angle Q, it's the angle theta. Right, that's a theta there. Sine theta over 6 equals sine 110 over 20. That means that sine theta is 6 sine 110 over 20, and theta is the inverse sine to the -1 of 6 sine 110 over 20. Calculator out, calculators to the fore. Now I'm going to do the inside part first. I'm going to go 6 times sine 110 equals that, divided by 20 equals that. That's good. Now, the inverse sine of that number, second function, sine of my previous answer, equals 16.37. What does it say to the nearest degree? 16 degrees. Excellent. And here's another example. From a point P, a ship is sighted 12.4 kilometers on a bearing of 137. So 137 is down here in what we call the 4th quadrant. Okay, if it were on a clock, it would be somewhere between 4 and 5 o'clock, I suppose, if 12 is not. Now, P. So here's P. Remember, I like north arrows everywhere. Now, 137 degrees is down here somewhere. From P, I can see my ship S. Put my little north arrow there as well. Now, this is S. I have 137 degrees here. Right, which means that I'm just going to fill things in as I go along. Right, these are going to add up to 180, so this is 43 degrees in here, and that's 12.4 kilometers. Alright, so far so good. A point Q is due south of P and is a distance of 31.2 kilometers from the ship. Okay. Now, what I have is somewhere, probably haven't given myself enough room here, somewhere down here I have another point Q, Right, another point Q down here, and that's 31.2. The bearing of the ship from Q. So here's my ship. That's not theta, that should be Q. Right, the bearing of the ship from Q. So that's this angle here, that's what I want to find. Now, I have a triangle here. I have two sides. For the time being, that's all I have. I don't have any of the angles. Right, I want to, if I can find two angles, I can find the third. If I've got the angles, I'll be fine. Now, I can determine the size of this angle here fairly well. Right, this angle here, 137 plus something equals 43, and in fact they're alternate angles here as well, so let's put that 43 degrees in here. Okay, now I've got this helpful property going on here. There's my angle on the opposite side. I've got this angle, right? Unknown angle here and the opposite side, so this is nice. Sine theta over 12.4. Sine theta over 12.4 equals sine 43 over 31.2. That means that sine theta is 12.4 sine 43 over 31.2. Theta is the inverse sine of that, of 12.4 sine 43 over 31.2 equals. Now 12.4 times sine 43 equals, divided by 31.2 equals this. The inverse sine of that answer is equal to this, 15.7. So that's closest to 16 degrees. Right, so theta equals 16 degrees. The bearing of the ship from Q. Here's Q, here's my ship. My ship, my bearing is measured from north in a clockwise direction. Right, so that's 16 degrees. There we are, done. Nice. Well, that's going to do us for this video here. There's quite a lot there now, but that's the sine rule. It's wonderfully effective if you can get two sides, two angles, right, or a relationship between them. Okay, see you in class.